The impulse-momentum relationship tells us that when an impulse is exerted on an object, a change in the object's momentum occurs. So you know that if you exert an impulse on a stationary grocery cart, the cart will gain momentum. Or if you exert an impulse on the cart while it's moving, you'll further change its momentum. Let's refine this a bit. The impulse that changes the momentum of something has to be an external impulse. Only an external impulse changes momentum. If you sit in an automobile and push on the dashboard pushes back on you. There is no net impulse and no change in net momentum. Internal impulses always cancel. To make the auto gain momentum, you'd have to get outside and push from outside. Only an external impulse changes momentum. Now here's the interesting part. If no external impulse is exerted on the auto, no change in momentum occurs. None. No change in momentum means that a stationary auto remains stationary, and a moving auto continues in whatever motion it has. The same is true for cars, grocery carts, or whatever. No impulse, no change in momentum. This relates to inertia in Newton's first law. Now consider a cannon being fired. Let's look at a snapshot of the ball partway down the barrel. While a force pushes the cannonball, an equal and opposite force pushes back on the cannon, which causes its recoil. Since this pair of equal and opposite forces occur for the same length of time, the impulses are also equal and opposite. So impulses relate to Newton's third law. This pair of impulses is internal to the system consisting of the cannon and the cannonball. Internal impulses don't change the momentum of the system. Before firing, the system's at rest and the momentum is zero. After the firing, the net momentum, or total momentum, is still zero. You can imagine the cannon recoiling somewhat to the left with the same amount of momentum as the cannonball. Net momentum is neither gained nor lost. So we see the cannonball's momentum is mainly velocity, while the cannon's momentum is mainly mass. So although both the cannonball and cannon each have momentum, in the combined cannon-cannonball system, and being vector quantities, they cancel to zero. We say total momentum is unchanged, zero before firing and zero after firing. In any interaction where no external impulse is exerted, momentum remains unchanged. We say momentum is conserved. We call this the conservation of momentum. In the absence of an external impulse or external force, the momentum of a system remains unchanged. Momentum conservation and the role of systems are nicely illustrated in the game of pool. I think we've all marveled how a cue ball comes to a halt when it collides head-on with a stationary 8-ball, transferring its motion to the 8-ball. When contact is made, consider the system consisting only of the 8-ball, the 8-ball system. When a cue ball strikes, there's an external force on the 8-ball, which then gains momentum. Let's look at this from the point of view of the cue ball system. When the cue ball strikes the 8-ball, a reaction force by the 8-ball, which is external to the cue ball system, changes the momentum of the cue ball. It brings the cue ball to a halt. Now let's look at this from the point of view of the combined 8-ball cue ball system. In this larger system, the forces we've considered are internal forces. No external force acts on the system. So there is no net change in the system's momentum. The momentum before the collision was mv, and the momentum after the collision is still mv. Momentum has simply transferred from the cue ball to the 8 ball. The